Good afternoon, everyone. My name is Ibrahim Shitu, and I'm representing Group 6. So today, I'll be presenting the introductory part of our final project is titled Simulation of a Deadlock Detection and Recovery for Distributed Database Systems. My colleagues, Hakim and Chachi, they also worked on this to tackle a critical issue in distributed computing. Next slide, please. So to start with an overview, in modern distributed databases, transactions constantly compete for shared resources. A deadlock then occurs when two or more transactions end up waiting for each other indefinitely to release these resources, which causes a circular dependency. So a transaction occurred from step A to B. So B is waiting for A to complete, whereas A is also waiting for B. So now this is a deadlock because they're both waiting for each other. So this is like a cycle, and then they keep on waiting. So now what our project aims to do is to simulate this specific environment by demonstrating not just how to detect these jams, but also how to actively recover from them using algorithms that prioritize system efficiency. Next slide, please. So moving to the background, managing these logs across different nodes or servers is it's very complex because there is no single global clock or state. So traditionally operating systems manage logs, but they often lack the tools to visualize why a halt is happening, like why the stop is actually happening. So to solve this, we are actually visualizing it by using the wait for graph algorithm model. So what this model does is that for every transaction, it is a node, and then for every dependency, it's like an edge. So this allows us to mathematically visualize exactly where the circular dependencies form, and then turn an abstract problem into a detectable cycle graph. Next slide. So the objectives of our project is to we set out to build a model lightweight Python simulator that actually accomplishes three things. So the first thing is to model distributed transactions realistically. The next thing is to implement algorithms that automatically detect these cycles. And then finally, we design a cost-based victim selection strategy. So this project is significant because it bridges the gap between theoretical operating system concepts, and it provides a visual tool that helps students and researchers to actually see this deadlock and then understand the cost of fixing it. So finally, for the problem statements what we're addressing is that in real-world distributed systems, manual identification of deadlocks is slow, it is error-prone, and then it's often impossible due to asynchronous communication. Existing theoretical solutions, they often lack quantitative tools for analysis. What our simulator does to address this gap is by providing an interactive automated environment where we can identify the system hangs instantly, and then also apply recovery strategies that minimize the data loss, which ensures that the system remains reliable and performant. So Chachi is going to discuss about the literature review and some related works.
Thank you, Ibrahim. I'm Chachi, and I will discuss about related literatures. First, let's see existing detection approach. The wait for graph approach models the dependencies between transactions. The age chasing algorithm is another major technique. We also have timeout-based methods. Next, once a deadlock is detected, systems must recover. Rollback and restart is one recovery method. Victim selection determines which transaction gets terminated. Next slide. Now let's look at what previous studies have contributed and where the gaps are. Prior researchers largely focus on single node simulation. Some models are able to detect deadlocks by the step short of implementing actual recovery strategies. Another limitation is that very few studies include data visualization. Our project addressed these gaps. First, we integrated cycle detection using Networks X built-in find cycle function. Second, we incorporated cost-based victim selection. And finally, we provide visual performance charts like the example shown here, which compares detection time and recovery time across different transaction loads. And Akim is going to take from here.
Yeah, thank you, Chachi, for that. I'm going to take over from that and present it. My name is Akim, and I'll start presenting that one on the technical aspect of this project, which is start from slide 8. And I'll talk about the system architecture and that made up this the simulator that we're talking about on this project. So our simulator is organized into 5 main components that works together. As we can see here, the entire project runs on Ubuntu 22.04 inside a virtual box which is a kind of a stable and an isolated environment, virtual environment, to be sincere, to be safe. So within this system, the simulator is structured into 5 main components. The first one is a transaction manager, as you can see here. So we have in one of the configuration managers Python scripts. So which is the main.py. That is where we have the configuration files. So this basically curates and manages transactions. And the next module is the lock manager. So this part of the module is kind of a function that manages the wait for relationship, and it controls the lock acquisition and release for resources like R1, R2, etc., as shown as you can see on this slide, on the slide 3. So the next one is on deadlock or the detector. So we also have this in the main.py script. It also uses the wait for graph through the network x.find_cycle functions, which is used to detect the cycle that was shown in slide 3. As well, the next one is on the recovery module. And this is available in result.py, or we can also find it in the result.recovery.py. So which are part of the configuration files in the project folder tree. So this basically selects a victim to terminate, which is cost-based, and remove it from the graph. So the last in the module we have it is the logger and the visualizer. So this is available in the recovery underscore metrics.py and visualize underscore metrics.py. What it does is that the two of them, they're responsible for saving all results, such as the metrics underscore log.csv or metrics underscore chart.png and so on and so forth. We have them in the configuration files that we're submitting. So these are the internal Python's modules that coordinates to detect, resolve, as well as record the deadlocks efficiently. So moving to the next slide, this is where we talk about the tools and technologies. So for us to be able to implement the simulator perfectly, we use several technologies. We use several tools and technologies in which the main language we use is Python 3.0. So everything is built and tested inside this Ubuntu 22.04 running on the Oracle VirtualBox. So we use the Network X library to build and analyze graphs, and that's how we're able to detect cycles that represent deadlocks. So for graph visualization, we use matplotlib, and as well for storing results and metrics, we use CSV and Excel files. So this combination made it easy to detect, not only that, visualize as well as evaluate the system performance. So here I'll be talking about the algorithm setups. So let me have having a quick rundown of how our simulator works step by step. So we start by initializing the transaction and resources. So next we build a wait for graph where each edge represents one transaction waiting for another. And the system this time around checks the cycle by the use of network X find underscore cycle function. So once a deadlock is detected, the recovery module selects a victim based on the lowest resource cost, and that victim is eliminated, thereby freeing up its resources. So finally, we visualize the before and the after graphs, and also log the performance metrics automatically, which are all included in the final documentation of this project. Now on this slide, I'll be talking about the implementation and results. So if you take a look at what the simulator actually produces, as we can see on this slide, from figure 1 to 3. The figure 1 is a kind of a graph that shows a deadlock situation. You can see that the circular arrows among transactions and resources, that's the wait for graph showing the cycle that we're talking about, that Ibrahim was talking about in the slide 3. So here on fig 2 is after recovery graph. The cycle is no longer there. As you can see, the cycle is no longer there. The simulator resolve the deadlock by terminating the victim transactions and releasing its lock. Those are the green cycle that you can see. So on the figure 3, so we have both. So it shows a comparison graph, which puts both the conditions side by side. So that is the before and after recovery, which shows how the cycle was successfully broken. So each of these results was generated automatically when running the main recovery script. So moving on to the next slide, this is where I'll be talking about the performance and evaluation. So here on our performance evaluation, the chart here compares the average deadlock detection time and recovery time for different number of transactions. So as you can see, the orange line represents the recovery time, and the blue line represents the detection time. So the result shows that recovery is slightly faster, and this is achieved with the help of our cost-based victim selection algorithm, which minimizes overhead when resolving the deadlocks. So these charts automatically generated by the visualize metrics.py script, and as well save it as metrics underscore chat.png in the results folder. So moving on to the next slide. Yeah, so this is where we'll be able to wrap up everything as we have seen in the previous slide. On the previous slides, our simulator have successfully demonstrated how deadlock detection and recovery work in a distributed systems. So it was able to detect cycles, chooses the best victim to terminate, and visualize the result through clear graphs and performance charts. So as you can see in the project folder tree, that is shown here. It comprises of the result folder. Not only that, the source code folder as well as the doc file, doc folder, where all are neatly organized for further analysis. So for future improvements, we plan to, or anyone who is interested in doing that, we will need to connect the simulator with the array databases like MySQL or PostgreSQL, and adding more recovery algorithm like one wait or timeout, and also build a kind of a graphic user interface, GUI dashboard, using the Tkinter or PyQt for the real-time visualization. So thank you for watching this presentation. We hope this project helps others to understand how operating system and database handles one of the most complex challenge and deadlock